if you're taking a course in thermodynamics, if you're brand new and you're working on homework problems, let's say from chapters 1 and 2, this is going pretty good. I'm seeing how to do this pretty good, and um, okay, I don't really need any tips on problem solving. I know how to solve problems, and maybe then you get into chapter 3 and you're starting to read problems and they're starting to look maybe a little different, and you're thinking, gosh, this is a lot harder. I don't know where to start, or I don't know how to start. What I want to do is I'd like to give you some tips on problem solving. And uh, let's look at some of those tips, and I hope they'll help. So here we go. I'm going to try to make 3 different videos. This is going to be part 1. And then in parts 2 and 3, I want to just go through, work out a couple of problems from start to finish to show you how I use the problem solving recipe, basically that I picked up from all of my professors when I was a student. So this isn't exactly a tried and true rote recipe. Um, it's something that where I've taken from a number of folks that have been my instructors or professors. So here's what I'd like to cover. First is, what's a recipe in general? And then what's a problem solving recipe? And you're going to see it's just very basic. And so most of the time will be spent on, well, what are the recipe steps? And then finally, I'd like to review some things which I want to suggest you not do. Okay, so what's a recipe in general? So of course I Googled it, and I got 2 very meaningful things. One is a recipe is a set of instructions. I think that's good. And it has to do with cooking. It's a set of instructions for preparing a particular dish, like cooking. But it is certainly a set of instructions. And then the second definition is something which is likely to lead to a particular outcome. And I really like that in general, right? Because what's the outcome you're praying for? A couple of things. You're hoping that the problem you're solving is going to look really good and you'll get a good grade on your homework score. But also, even a better outcome is that as you get better and better at solving problems, writing down your solutions, you're preparing to do well on your quizzes and your tests. And so I like the idea of a recipe, something that's likely to lead to a particular successful outcome. So have you ever followed a recipe for doing anything? Well, here's my example problem, is cooking chocolate chip cookies. So I hope that everybody's had some experience in this. And so you've downloaded a chocolate chip cookie recipe, or maybe someone shared the recipe with you. There's your ingredients. Here's the steps you take in preparing the ingredients and the steps you take in cooking. Okay. And so you may have done this a few times. And as you look at your recipe, you think, I might have a better idea. I might like to adjust that recipe. So you say, oh, I'm going to add some more chocolate chips because I like chocolate chips. Cookie tossed a little, maybe salty. I'm going to reduce my salt that I use. Or I might want to add to the recipe. I might want to add pecans, or even better, add macadamia nuts. Or you've had some experience, I might need to cook these cookies a little longer or a little shorter. So you're either adjusting your recipe or you might be adding a couple of things to your recipe. And so here's my claim is that for any recipe that I'm going to try to tell you here in a minute, don't hesitate to adjust the recipe or add to the recipe if it works for you. Because as a reminder, the work that you're doing in your class, or if you're cooking, so your work, whether it's cooking or problem solving, in a class or beyond, your work is a representation of you. It's not a representation of the recipe. And so that's sort of an important takeaway. Don't hesitate to, these are just ideas for you to explore and think about, and then adopt what's going to work for you. Okay, so now what's a problem solving recipe? So I'm going to disclose to you my recipe that I recommend. It's going to be step 1, 2, 3, 4. Going to look easy. And so here's the recipe I recommend. Step 1, read the problem in words. Step 2, draw a sketch. Always start with a sketch. Step 3, plan your work. And step 4, work through the solution. And you think, oh, gee, thanks a lot for that. I never could have figured that out. Well, the devil's in the details. And so I want to provide some more details about each one of these 4 steps that I recommend. Okay, first, step 1, read the problem start to finish. And so I've picked out a homework problem that was assigned just recently in one of the thermodynamics class sections. So I will read the problem out loud. At the grocery store, you place a pumpkin with a mass of 12.5 pounds mass on the produce scale. Okay. There's a spring in the scale that operates so that for each 3.7 pounds force applied, the spring elongates by 1 inch. Okay. If local acceleration of gravity is 32.2 feet per second squared, what distance in inches did the spring elongate? And so that was a real problem. And I bet you think, oh man, I've either had that problem, I've solved it, but it looks pretty easy. So let's go through the steps. Okay. The first is we're going to read the problem carefully. And so we're going to say, well, what's wanted? What's the problem asking us to do? And also we're going to look for some key words or clues in the problem statement. So we fished out what's wanted. Well, what distance did the spring elongate? That's what you're looking to calculate or show how to find. Okay. As you read carefully, let's see, mass is given. Keyword, spring scale, spring scale. So it's going to involve a spring scale with a known load, 12.5 pounds mass changed into the weight, and it stretches the spring a known amount. And probably in your mind, you say, I've had some previous course experience with springs, or maybe even high school physics. So I think I know how to get started. So step 1, we've read the problem, find out what's wanted. We've looked for some keywords. Next step, start with a sketch. Always, always, always start with a sketch. There's some good reasons for that. So what would your sketch look like? Your sketch does not need to look like a work of art like this is, right? I've taken the time to show I've downloaded some pictures of springs, and I've created, using PowerPoint, this beautiful sketch. Hand drawn is fine. Your sketch does not need to be a work of art, but you get the idea. So draw a sketch good enough to give somebody else and yourself a good idea. So here's the unstretched spring. I've shown a force F naught, sort of the initial very small weight of the spring, maybe the hook itself. Okay. And then here I'm showing my pumpkin attached to the spring with a new force, F spring. And I've refreshed my memory from either high school physics or a previous freshman level engineering course. And I've written down that governing equation on my sketch. Okay, so that's my sketch. For this problem, that's going to be good enough, isn't it? Now, as you move into chapter 3, you're going to be seeing, I think I might have to draw several sketches. And we'll talk a little bit more about that in the next couple of videos. All right, so you get the idea. Start with a sketch, okay? Now, the reason we start with a sketch is the next step is plan your work steps before you start putting the pencil to paper, except for that sketch that you drew, okay? And I got to tell you that I find that drawing a sketch helps me plan my work. And so that's been a real plus for me as a student and then as a practicing engineer. And so plan your work steps. What does that mean? What steps do I need to take to determine what's requested? No more, no less for time management. What fundamental relationships apply to my problem? And so when I was drawing my sketch down, you saw that I sort of wrote down the fundamental relationship for the pumpkin weighing problem on my sketch. Okay. Next thing is, once we've got that fundamental relationship, what are the variables in the formula? Are there any that are still unknown? And if so, how will I determine in my fundamental relationship if there's some things that still aren't known, that aren't what I'm looking for? How will I determine those first? Okay. And then in this little mental planning thing, plan the order in which you do things. So you don't have to write things down. You don't have to write down your plan. Just get it in your head. And so in fancy mathematical speech, for most thermo problems, how do I get to one equation and one unknown? That's the trick, really, right? So it'd be mathematically speaking, I need to get one equation and one unknown. There will be some more complex problems, and certainly will be subsequent courses. How do I get to n equations and n unknowns? But for right now, let's not worry about it. And most of your homework problems are going to be one equation and one unknown. How do I get that thing solved for the variable I'm looking for? Okay. Now work through the solution. Now is where after you've drawn your sketch, put down pencil and paper. So the last block, step 4, work through the solution, showing your work with pencil and paper or electronically, however you're solving the problem. So I kind of went back to step 2. Start with a sketch, doesn't need to be a work of art. The given information is depicted in the sketch. Any fundamental relations that you know off the top of your head depicted in the sketch. And it might be several sketches depending on the situation. Really important. So that's going to be the first part of work through your solution. All right. The next idea, work down the page. I didn't used to do that as a student, but I did get better and better at it as I lost credit for working all over the page. So I learned to work down the page to maximize my partial credit. And boy, that really paid off for me once I became a practicing engineer. Work down the page. Paper is inexpensive. And so don't hesitate to use multiple sheets of paper in solving a single problem. Work down the page. Write down in your solution the governing fundamentals, and then enter numerical values. I see a lot of folks just starting scratching down numbers. Write down the governing fundamental equations first, and then start applying your values to that fundamental equation or equations. Units are as important as values in thermodynamics class and many other classes. So you must be writing out units throughout your solution. Okay. At a minimum, use some common sense. Writing out units that are in the important steps of your solution. That helps you cancel your units out to get the right units in your final result. Explain your work in a few phrases as you go along. So, for example, for those of you early in the class, it'll be Greek to you. A phrase might be, use the first law. Okay, well, you might not have had that yet, or you may have been exposed to that. Or using a free body diagram, or drawing the free body diagram, or upward and downward forces must balance. Those are just some key phrases that will help you in writing those things down in your solution will help you and also maximize partial credit. Explain your work in a few phrases as you go along. Okay. Let's say, great, you've done all of that work, you've gotten to a final result. Make your result clear to the person looking or evaluating your work. Come up with your own style. Either box it, or circle it or underline it with a number of lines. Make it clear what the result is with units. So make it clear to everybody, including yourself, that you've gotten to a final result and you're showing what that final result is with units written out. That's the recipe. Now, some ideas on what to not do. So this is what I would recommend you not do. It is tempting to go into a textbook or class notes and find a formula. And I've, as a student, I've been guilty of this. So because it's so tempting to find the formula, right? Find a formula in the book that looks like it'll work, write it down, apply your numbers, circle the answer, and you are done. That is not a good approach for problem solving. That doesn't prepare you at all for success for quizzes and tests. Don't succumb to that temptation of what's the formula. Here's another thing that you shouldn't do. The problem statement already included a sketch, so I don't need to show a sketch. Big mistake. So even when a problem statement includes a sketch, strongly recommend, it doesn't have to be a work of art, but redraw a sketch because you're going to want to add some things to that. I can almost guarantee that your sketch is going to need to add some notes or given information or something to the sketch that was included maybe with the problem statement. Problem includes sketch already, so I don't need to show a sketch. Don't fall prey to that. Okay, so here's another one. I found the solution manual for my class online, or somebody shared it with me in PDF format. I'll just copy that solution, be done with it, circle that answer, and I'm done. I recommend you don't do that. You'll get credit for your homework for doing it, of course, sure. And that'll be 10% of your grade. Really don't recommend that because you're not training yourself to solve problems that way. You're just regurgitating probably a crappy solution that somebody else wrote down. Some graduate student was assigned to create the solution manual, and it's probably not a very good solution anyway. So I'll just copy a solution from that solution manual. Bad idea. Okay. And then the worst idea of all is I'll copy somebody else's work in my class and I'll turn it in for credit. That's triple X, right? Because that's a violation of the honor code. So two things wrong with that. Violation of honor code, reprehensible thing to do. Another thing is you're really not training yourself to solve the problem. You're using somebody else. You're claiming somebody else's work as yours. Not a good idea. Okay, that's the recipe that I recommend. I hope it helps you. So let's see. Let's cover what we just covered. All right. Read the problem in words. Take a little time to do that. Next step, always start with a sketch. Always, because just drawing that sketch can help you plan your work. It can give you ideas on planning your work. Okay. This might be a little different than recipes that other instructors or professors have given you. But anyway, this is my recipe. See if it works for you. So once you've planned your work in your head, work through the solution. What does that mean? Work down the page. Paper is inexpensive. Write down the fundamental equations. Show and explain your work. Units are as important as values. Strike out, cancel out your units. So you're working carefully with units to get the final result in the units requested to be sure units are consistent. And then explain your work in words. Look like I've got that a couple of times. Does not have to be a paragraph, doesn't even have to be a sentence, just some phrases within your solution. It helps you go back and look at your solution as you're preparing for a test. Okay, helps you because you'll forget what you did after a couple of weeks. Here's my solution. Okay, that brings us to the end of this video. So what did I try to do? I tried to offer a recipe for problem solving that has worked for me. It paid off for me as a student. And then it paid off for subsequent courses in the upper levels, like at senior level. And then it prepared me to become a practicing engineer as well. And my little recipe is the combination of what a number of professors um, guided me into. Now, that start with a sketch thing, that was a common denominator in mechanical engineering at Virginia Tech. Gosh, just about every instructor I encountered in all the different classes, almost all of them were talking about start with a sketch. So that's an important part. Okay, I hope that helps. Next two videos. The next video, part 2, is going to be an easy problem that would be representative of chapters 1 and 2, maybe. And then the third video is going to be a chapter 3 problem. Okay, I invite you to continue on watching the next videos.